Hello, it's Keith here, and this is lesson 4 of the simple series of my 6809 assembly programming tutorials. And today we're going to be looking at the FM7, and we're going to have a simple example, or relatively simple, to get a smiley face. You can just about see it over there, it's very small. We're going to be moving that around the screen with the joystick, so we're going to be able to control it. It's a single self-contained example, that's what the simple series is. So hopefully you can take this and modify it and do your own things with it. Now, before we do, let's go over to my other screen, my zoomed screen, because the example is set to be very small, which isn't so great for us actually seeing what's going on. So here it is. So you can see here, there's our smiley. It's 3 colors. Now the FM7 is an 8 color system. It uses 3-bit planes, so that's why we've got 3 colors in our smiley here. And we're using XOR, so as it moves around the screen, you can see if I can have to chase it with my mouse because the window doesn't update otherwise. So you can see here that basically it's disappearing, but if you catch it very quickly, you might notice that parts of it are disappearing and other parts are reappearing. It's XOR, so when we draw the sprite to the same location twice, the second time we'll invert it, removing it. It's a simplicity. Basically, it means I don't need 2 different versions of the sprite routines, one to draw a blank sprite, one to draw the smiley. We can XOR it, we can take it off very easily. Now, the tricky thing with the FM7 is, you may know, is that the FM7 has 2 processors. They're both actually 6809, not that that matters, because the sub-processor has its own ROM code which does graphics, and we have to tell that sub-program what to do. So today, the program is going to be specifically configured to draw an 8x8 sprite. If the sprite was very large, we'd have to break it up and send it in packets, because each packet that we send to the sub-CPU has to be 128 bytes, including the command. The point I'm getting to is if you want to see non-XOR, if you want to see big sprites, please see my other example on FM7 graphics where we went through almost all of the graphics functions that you can send to the sub-CPU and how they're affected. And I've actually done an example where we wrote our own program and transferred that with the secret commands to the sub-CPU processor to draw sprites very quickly. So this is just a very simple getting started example if you want to have a look at this system. I've talked quite a lot there. Let's go over to the source code and let's have a look at what we're working with. Okay, so here is the code we're going to be looking at today. So this is FM7 bitmap. So the way I'm writing my programs for the FM7, I'm transferring them to a disk, but we're actually creating the header for the file ourselves, and so you can see that just here. Now our program will run from memory address 2000 in hexadecimal, but our header is going to start first, so we're subtracting 21 here from hexadecimal 2000, and we've then got our header here. Now these are all bits of byte data. We've got a program start, a length of the program, and a few fixed bits of data there, but we've got this padding off, and that's important when we're defining data in this way. The assembler I'm using will pad to a 16-bit boundary, so it would be potentially adding 0 bytes on lines like this, which are 3 bytes, which annoys me and makes me extremely angry, and I throw things, and it's not good. So we're turning padding off to avoid all of the damage that could occur there. So that's going to make me a lot happier. So that's what we're doing. Now we're also including a footer. Now I'm not actually sure if we need this. It seemed to work when I took it off, which was a surprise, but the file should have a footer, so we're creating one. It's got the start address here, and it's got an EOF byte here. And so this is all going to be built, and it's going to be transferred to the disk. You can download the build scripts and the source code for today's example, but the build scripts more importantly from my website, so you can build this yourself and run it pretty easily, hopefully. On the Hello World series, I did go into more detail about how to build the disks and things, so if you want to see more detail on that and how to use the assemblers and things, please take a look at that. We're just looking at the code today. Now, there's a few complexities with today's example, or there are, but the first is when we're reading the joystick, we have to negotiate with the AY sound chip. Now, the AY sound chip has 2 built-in data ports, and we use one of them to select the joystick we want. We're actually using joystick 1 here. My emulator on this machine seems to be configured to 1. On the other machine, it was configured to joystick 2. I don't know why that happened, but anyway, we've changed it from joystick 2 to joystick 1 today. So it just changed the byte there, but we have to select the port we want to read from the joystick port, and then we have to read in, and we do that through the AY sound chip. And so we've got these commands here to negotiate. There's one there and there's one there to negotiate with the AY sound chip. So we're going to see them. And the other thing is, as part of the sprite drawing routine, we need some commands to negotiate with the sub CPU. So we've got these commands that we're going to have to look at, and we're going to look at the FM1s first because they're pretty simple, pretty self-contained. So there are basically two ports we have to work with: FD16, which is a data port, and FD15, which is a command port. And so if we want to select a register, we would write to the data port, and if we want to read back from the selected register, we would also use the data port. But we need to send a sequence to the command port, and so we've got that here. We have to sort of write these numbers here and some zeros. I'm not going to go into it. It's just what you have to do to select a register or to read one. So you can see here we've got this command for reading the value of a register, and we specify B as the register number, and the returned value will be in A here. Or we can write a register, and we do that with these, and we will specify the register number in B again, and the new value that will be written in A. So these are doing the selection and the reading and the writing of AY registers, and we're not making a sound with them today, we're just selecting the joystick. So that's what we're doing here. So we are using AY register 15, which is joystick select. Now on this machine, I'm selecting joystick 1, so we send 2F. But if we were using joystick 2, we would use 5F. We just send a different code there to select the joystick. And then we read in from register 14, and we will get the bits representing each direction, whatever one of the joysticks we selected. So that's how we use that. As I say, we just need a command to deal with the complexity of reading and writing those AY registers. Now, the next thing we're going to be looking at is the more important or more significant show sprite routine. So we're going to show a sprite to the screen. As I say, we can't access the video memory directly. What we have to do is we have to negotiate with the sub-CPU and ask it nicely, and hopefully it will do the work for us. The way we do this is we transfer some bytes of memory to the shared area. This is at FC80 on the main CPU, but actually appears at a different memory address, D380 on the sub-CPU. If you're programming the sub-CPU side, or if you're referencing your own data that you've transferred, well, you would need to do that. But today you don't need to worry about the sub-CPU's memory address. It's only the main CPU we need to worry about. So we need to send two things. First, we need to send a command, and this is a sequence of bytes in the correct format. And then we need to send the actual data for the command to work with, at least for today's example, and that's the data here. So the command is in a pretty fixed format. Now, the example today is quite unique. It's very small, the data we're sending, so we can send it in a single packet. If we were doing a larger graphic like the 48 by 48 Chibico bitmap we did in the other example, you'd need to use multiple packets, and you would need to specify a continue command here, and you'd need to use another command to continue drawing the bitmap. But today's will fit in a single one, and this is a single block example. We use command 1E, which is the put block 2 command, and that's what's going to draw our sprite for us. We specify a start X and Y position, which is in pixels, and we've done that here. We're going to modify these. We've got these addresses. We're going to change this in RAM. So this is the start X and Y. This is the end X and Y. And then we've got an unused byte here, a function number, and the number of bytes that we need to transfer, which is 8 lines times 3 bit planes. Now, the function for means XOR, and this means if we draw something, it will invert what's already there. This is great for this example because if we draw it twice, it disappears. Now, if you were doing lots of graphics and some overlapped, it would get really ugly, but I think XOR is a great way to get started because you don't have to worry about how to redraw the background that your sprite goes over. And there were loads of games back in the day that used XOR to fantastic ability. The game Destructo, the Island of Dr. Destructo, was a fantastic action game that used XOR. The Dizzy games, I believe, they used all XOR. They all used XOR. It's a good way of doing things, and I think people avoid it because it can be ugly if you've got things overlapping. But it's also very easy, and you don't need multiple buffers to do your graphics. So it's definitely worth considering in some cases. So that's our command, and here's our bytes, and the format we need to send in is in blue, red, green format. So we've got 3 bit planes here, and you can see there's the circle of the smiley, there's the mouth of the smiley, and there's the eyes of the smiley. Now, if you reconfigured the colors, the bit planes would be in a different order, but there's no need for you to do so. You can't create new and unusual colors. You can't have all of them as a shade of pink, for example, all 8 colors. Not on the basic FM7. I think the FM77 could do that, but it's only bright primary, so you'd have no real need to remap the bit planes, really. So that's the data we've got to send, but we need some commands to negotiate with the sub-CPU. Now we need to transfer our data that we just saw to FC80. We've got a command send and send alt here. These are going to transfer data for us. Now send alt will allow us to specify a different starting point within the shared memory range. We're going to be using those, but we also need to stop the sub-CPU and release it, and we also need to check if it's busy before we stop it. And communicating these kind of things is all done with FD05, specifically bit 7. Now if we test bit 7 and it's a 1, then the sub-CPU is busy. We're testing that with a branch of minus here, because if the top bit is 1 then the value is minus. So that will wait and see until the sub-CPU has finished whatever it's doing. Now if we actually write to that same address, then by setting bit 7 to 1, we will actually stop the sub-CPU. And by writing a 0 to that top bit, we will release it. And when we release it, the ROM will restart and it will start looking at what's in its shared memory and it will process it. And so if we've given it proper command in that memory, it's going to work very nicely. And if we put a load of garbage in, it's going to get very angry and crash. And that won't go well for us. So we're going to be using those and we're going to be transferring the data. And you can see that here. So what we're doing here is we're updating the X and Y position in this show sprite routine, because we're going to call this with an XY position. We want that smiley to appear. So we're updating those just here. And then what we're doing is we're calculating the endpoint. And I think I can spot a bug here because, oh, it's not a bug. But anyway, it's calculating the end position by adding 7 using this load effective address plus 7 to X. That's effectively an add 7 to X command here. And I've put add 8 there, so that should be a 7. But these values are just sample values. They never actually get used by the program. They're just placeholders, really. But it should have been a 7 there, I think, so that it matches the sprite that's actually going to be shown. So that's updating the parameters of the data we're going to send. We're then loading our bitmap data here. We are loading the address of the put command, the length of the put command in words. That's why we're dividing by 2. My send command works in words. We're halting the sub-CPU. We're sending the command to the sub-CPU. We're then sending the extra data, that's the bitmap data. We're sending that to the sub-CPU as well. It's basically being tagged onto the end of the command, which is why we're using a different command. We're not starting again from the start of the range. We're continuing from the last one, so that's why we're using that alternate command. And then we release the sub-CPU, and the sub-CPU will now process that graphics command and get the smiley on the screen. Now it's a little bit slow doing this, I'm not going to lie. We can get around that by writing our own more efficient program on the sub-CPU, but the benefit we have for this is the sub-CPU will be drawing that bitmap while our main CPU is working on other things. So it's multi-processing really. So our main CPU could be playing some music while the graphics are still drawing. You do have to design your game in a way that will work efficiently with that, but as I say, it swings and roundabouts in that although the sub-CPU is a bit slow, we can make it do things while our main CPU is working on other tasks. Okay, so we've got our sprite routine and we've got our function to read in from the joystick, and now it's time to put them to work. So we're showing the initial sprite position here. We're loading a value of 100, 100 into X and Y here and showing the sprite. Now that will put the starting position of the sprite on the screen, and then what we're doing next is we're reading in from the joystick and we're seeing if any direction has been pressed, and if it's not, we're going to wait until it is. So we've got a loop here. This is just going to continue until a direction is pressed. Now we want to remove the sprite from the screen because we might need to move it. So what we do is we draw the sprite to the screen again, and because it's an XOR sprite, that will remove it. So now our sprite is gone, and then we're processing each of the directions up, down, left and right. What we do is we check if that direction is being pressed, and if it's not, we skip over the next piece of code. That's this bit of code here. If it is being pressed, we check the current position of the smiley, and if the smiley is already at the limit of that direction, for example if it's already at the top of the screen, we can't move it anymore because it will go off the screen or it will make a mess somehow. So we skip over the next command. But if it can move, then we move it, and in this case we are subtracting 2, and there's another bug there. That should be y equals y minus 2 in that comment there. So this load effective address y comma minus 2 here, this is a trick. It's basically saying y equals y minus 2. We're just using the subtraction of an immediate there from the y register. Load effective address, it's kind of a cheat. We're using it as a sub 2 in this case, but it works very nicely. So there we're subtracting 2. There we're adding 2 from Y, and here's the X versions again, just checking the boundaries. 640 by -8. 640 is because the screen is 640 pixels wide, -8 because our sprite is 8 pixels wide, so we're just calculating the right hand side of the screen there, and in each case updating the position of the sprite if we can accordingly. Once we've got here, it's time to draw the new position of the sprite because it might have moved, so we do that. We then got a little delay just to slow the routine down so our sprite doesn't fly around the screen too quickly, and then we run our infinite loop here, and that will just keep running as long as we decide to run it, and that is how we move our sprite around the screen. So there we go. That's really all there is to it. It's a nice, simple little example. It's a bit of a pain with regards to controlling the sub CPU, but that's the name of the game with this system, so we just have to deal with that. As I say, you can go to my website, you can download this, and you can download a few other examples for the FM7 because it's a nice little system. It's not very well known. The documentation is unfortunately getting a little bit patchy here and there, in the sense of some of the documents I found I could only find in Japanese, but fortunately I could just about read them. I can't find anything on the FM77 though. I'd like some stuff on the graphics of the FM77, but I haven't really got enough detail to write any tutorials on it. I am keeping an eye open for a couple of books if I can find them, and hopefully we'll someday be able to cover that as well, but I don't want to do it with guesswork. I've got some vague samples working, but I don't feel I'm using the hardware right, so I'm hoping one day I can get some books on that and we can do some FM77 as well. Anyway, if you've liked this, please hit the like button, please go to the website and download the sources, and also if you would subscribe, that would really help me out, keep my motivation up for messing around with these weird systems some more. Anyway, hope you've enjoyed this. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.